Welcome to this explainer. Today, we are going to completely demystify the mechanics of modern authentication by digging into single sign-on, OAuth 2, and OpenID Connect. Look, over the last decade or so, we've seen an absolute explosion in the number of software-as-a-service applications and microservices that we use every single day. If you build software, if you handle user data, or even if you just want to understand the invisible locks on the doors of the internet, you are in the exact right place. We're going to break down the precise architectural frameworks that allow entirely separate systems to communicate securely, verify your identity, and grant access, all without ever once exposing the ultimate secret, your password. Here is our roadmap for today. First, the single sign-on solution. Second, we'll meet the four actors. Third, we'll walk through the authorization code flow. Fourth, we'll unpack access tokens. And finally, we'll look at app-to-app authentication. Let's get right into it. Section 1. The single sign-on solution. To kick things off, let's look at the growing pains of a fictional company, we'll call them ACME Inc., and the very real login dilemma they face as they scale up their operations. So, think about Acme Inc. They're an online retailer, right? They started out with just a simple web store, but they quickly expanded to include mobile apps, specialized internal dashboards, and third-party customer support tools. As they grew, they hit a massive wall. They realized their customers and their employees were being forced to manage multiple, unique sets of credentials for all these different disconnected silos. It's incredibly inconvenient, it's frustrating for the user, and honestly, it's a massive security risk. When people have to remember 10 different passwords, what do? They reuse the same weak password across all of them. But modern web architecture has actually solved this quite elegantly. Think about it. It seems almost like magic that today you can access a dozen different company tools or log into a brand new shopping app without typing your password into every single one. How does that actually work under the hood? Well, the answer to that is single sign-on. It's an architectural shift that has drastically reduced password fatigue for both employees and customers alike. Single sign-on basically allows users to authenticate just one time at one highly secure checkpoint and then magically gain access to a whole interconnected suite of applications. Just think about your daily workflow. When you log into your primary work email in the morning, and then say you click over to your company's HR software to check your time off, you're magically already logged in. You didn't have to type your password a second time. That seamless experience, that is single sign-on in action. But it's not just about user convenience. It is a fundamental structural improvement in exactly how we handle security across complex distributed systems. In the old days of web development, every monolithic application had to handle its own security entirely from scratch. Every app stored a copy of your password in their own isolated databases. The problem there is obvious, right? If just one of those dozens of apps got breached by a hacker, your password was out there, instantly compromising your accounts everywhere else. So the solution was a major architectural shift. We completely separated the responsibility of authentication. We literally took that job away from the individual apps and handed it to a centralized, dedicated security desk called the identity provider, or IDP for short. Real-world examples of identity providers that you probably use are systems like Okta, Microsoft Entra, or even Google. Now, instead of every single app checking and storing your password, they all rely on the central IDP to verify users through standardized protocols. The apps themselves, they never even see your password. Section 2. Meet the four actors. Now, to make this decentralized trust actually work in practice, we use an industry-standard framework called OAuth 2. Before we can really dive into the complex web of network redirects, we need to meet the cast of characters involved in this OAuth 2 framework. Think of this entire process like visiting a highly secure corporate building. First up, we have the user. Let's call our user Jenny. She is the visitor trying to get into the building to access her own files. Next is the client. The client is essentially the lobby of the building. This is the web page or the mobile app Jenny is actively interacting with, like the Acme storefront. Third, we have the identity provider, or IDP. Think of the IDP as the heavily armed security guard, meticulously checking IDs at the front desk. The lobby itself doesn't check your ID, the security guard does. And finally, the resource server. This is the locked office deep inside the building that you actually want to enter. It represents the backend database or application that holds Jenny's private data. Section 3, the authorization code flow. Now that we know who is involved, let's watch them run a digital relay race. In OAuth 2, the sequence of steps that allows a client app to access backend data is called a grant type. We are going to look at the most common and, frankly, the most secure grant type used for web applications today, the authorization code grant type. Imagine Jenny trying to access her private shopping list on the ACME app. She clicks View My List. The client app receives a request, but it basically says, hold on, I can't let you see this yet. I need a token to get your data from the backend. Go authenticate with the IDP. The app then literally redirects Jenny's browser over to the identity provider. Jenny types her username and password securely directly into the IDP. The IDP validates her credentials and redirects her back to the client app, but as it does, it hands the app a temporary, one-time use authorization code. The client app then takes that temporary code and secretly trades it with the IDP for a real access token. Finally, armed with that token, the client app presents it to the backend resource server, which unlocks the door and serves up Jenny's shopping list. So this entire exchange really boils down to 3 critical steps that build upon each other to create an airtight, secure loop. First, you have the front-end redirect, sending Jenny away from the app to the IDP so the app never sees her password. Second, the IDP sends back a one-time authorization code via the browser. And third, a highly secure back-end channel where the app quietly exchanges that code for the actual access token. It is exactly this separation of the public browser redirect and the private backend exchange that makes OAuth 2 so remarkably secure. Now, looking at this multi-step process naturally raises a glaring question. Why all the middlemen? If the identity provider successfully verified Jenny in step 2, why not just hand over the final access token immediately in the browser redirect? Why bother with this intermediate, temporary authorization code at all? Well, the answer to that comes down to the fundamental security mechanics of the internet. If the ultimate access token was sent out in the open browser redirect, it would pass right through the user's highly vulnerable browser environment. When things pass through a browser URL, they can easily get saved in your local browser history. They can be intercepted by malicious browser extensions. They can get captured in intermediate server logs or proxy logs. They are highly susceptible to man-in-the-middle attacks, literally just sitting there waiting for a hacker to snatch them. An access token is the master key to your data. By issuing a one-time authorization code instead, this extra step ensures that the actual master key exchange happens strictly hidden on the backend, directly between the client app server and the IDP server, safely out of reach of the user's potentially compromised web browser. Section 4, Unpacking Access Tokens. So the client app successfully executed the secure backend trade and got the access token. But what exactly is it? Think of the access token as your digital VIP badge. It mathematically proves to the backend resource server that the client app is fully authorized to act on the user's behalf, without the resource server ever seeing or even needing Janie's password. A really critical concept here from the OAuth framework is something called scopes. This VIP badge doesn't just grant universal access to the entire building. The token contains specific scopes that strictly limit what the app can do. For example, the token might have a scope that says the app is allowed to read Janie's shopping list, but absolutely under no circumstances is it allowed to delete her account or change her billing information. It's a precisely tuned permission slip. So how does the backend actually read this permission slip? Tokens generally come in 2 architectural flavors, opaque and non-opaque. Let's break down opaque tokens first. Opaque tokens are exactly what they sound like, completely random, meaningless strings of characters. They contain no actual data inside them. If a resource server gets an opaque token, it has no idea what it means. It has to pause, turn around, and constantly call the IDP back over the network to ask, hey, is this random string valid, and what scopes does it have? This process is called introspection. While it's highly secure because the IDP remains the absolute source of truth, it can become a real bottleneck. All those extra HTTP network requests can seriously slow the system down. Now, on the other hand, we have non-opaque tokens. By far the most common type used today is the JSON Web Token, or JWT. Unlike opaque tokens, JWTs securely carry their own readable data right inside the token itself, usually structured as a header, a payload containing the scopes, and a cryptographic signature. The IDP signs the JWT with a tightly guarded private cryptographic key before handing it out. When the resource server receives the JWT, it doesn't need to call the IDP back over the network at all. It can instantly, mathematically validate the token signature locally using a public key. If the math checks out, the backend knows for sure the token is authentic and hasn't been tampered with. This makes JWTs incredibly fast and allows backend microservices to scale and operate totally independently. But whether a system uses opaque tokens or non-opaque JWTs, there is a golden rule in modern authentication. Access tokens are deliberately given incredibly short lifespans. We are talking usually an hour or less, sometimes just minutes. Because apps continuously pass these tokens around across networks to access resources, there's always a slight risk of exposure. Keeping their lifespan incredibly short makes it much harder for a stolen token to be successfully misused by a bad actor. By the time the hacker tries to use it, the token has already self-destructed. Now, to prevent the user from having to log in manually every single hour, the IDP often issues a secondary, highly guarded refresh token. When the short-lived access token expires, the client app quietly uses the refresh token in the background to get a brand new access token, keeping Genie's session active without ever interrupting her workflow. Section 5. App-to-app authentication. Up until now, we've focused heavily on Genie, a human user, logging into an application. But what happens when a human user isn't involved at all? When backend servers need to talk securely to other backend servers, we use a completely different flow called the client credentials grant type. Notice exactly who is missing from this equation. There is no end user, there's no Genie, and there is absolutely no web browser to redirect. In this scenario, the Acme app itself authenticates directly with the identity provider. The Acme app hands over its own hard-coded client ID and client secret, essentially acting as its own username and password. The IDP verifies the app's identity and issues an access token directly to the Acme server. Armed with this token, the Acme app can now securely ping a third-party backend, like a payment service provider, to process overnight transactions completely automatically. The client credentials flow is amazing because it proves that the underlying protocols of OAuth 2 are entirely universal. It is purely designed for secure service-to-service, machine-to-machine communication. The app simply acts as its own user, using its own highly guarded credentials to secure an access card. However, because there is no human user involved to grant consent, this flow is considered highly privileged. A token granted via client credentials often has sweeping administrative access, meaning this flow should strictly be used between highly secure, deeply trusted backend environments, never ever on public-facing applications or mobile devices. So we have thoroughly explored how OAuth 2 acts as a fantastic framework for authorization. It hands out access tokens like VIP passes, successfully answering the question, what is this app allowed to do? But, and this is crucial, OAuth 2 has a massive blind spot by design. It was never built for authentication. It does not answer the question, who is the user sitting at the keyboard? If the Acme app simply wants to say, welcome back Genie, or display her profile picture, an OAuth 2 access token doesn't help at all. To truly identify the user, we have to layer a specialized protocol on top of OAuth 2, called OpenID Connect. OpenID Connect bridges this gap by introducing a brand new element called the ID token. When the client app trades its authorization code, OpenID Connect ensures the IDP hands back not just the access token for the backend, but also an ID token meant exclusively for the client app. This ID token is always a secure JWT, and it contains standard profile claims, like Genie's name, her email address, and exactly when she authenticated. It provides a universally standard way for the app to securely learn the user's actual identity. By combining the access power of OAuth 2 with the identity layer of OpenID Connect, we achieve the seamless, modern single sign-on experience that powers the modern web. So the next time you click a button that says Login with Google or Login with Microsoft, ask yourself, are you just asking a system to open a digital door, or are you handing over your digital passport?